All right, friends. Day 4 of Unit 5. Remember, Day 3 was a practice day, so if you're watching this the day after you saw Day 2, well, we missed a day, practice day in between. This lesson deals with integration by substitution. It opens up for us a broad class of functions that can be integrated. A broad class because we get to deal today with the chain rule in reverse. What happens when we're integrating functions that are compositions in reverse? How do we reverse the process? And we begin by underscoring the importance between du and dx. The difference between du and dx. And so I'm just going to play this game. Let's let f of x be x squared plus 2, and let's let u be x to the 5th. And I want to find 3 different things. I want to find the integral of f of x dx. I want to find the integral of f of u du. And I want to find the integral of f of u dx. These are 3 very different things, even though they look very similar. In the first case, the differential is dx, and that means that we're taking an integral where x is the variable. And our function is f of x. So this is an integral of x squared plus 2 dx. The integral of x squared plus 2 dx. And so what is that? Well, we take the antiderivative term by term, 1/3 x cubed plus 2x plus a constant. 1/3 x cubed plus 2x plus a constant. That is a very standard problem to know how to do. In the second problem, the differential is du, which means we're taking an integral with respect to u. U is the variable, and our function is a function of u. So what is f of u? That's u squared plus 2. And so the antiderivative appears to be very similar. That's 1/3 u cubed plus 2u plus a constant. But what is u? U is x to the 5th. And since u is x to the 5th, this is 1/3 x to the 15th plus 2x to the 5th plus a constant, which is a very different answer indeed. And then in the third problem, the differential is dx, but the function is in terms of u. So we're integrating u squared plus 2 dx. But we can't do that. We have a differential, that's dx, but our function is in terms of u. Luckily, we have a connection. U is x to the 5th, so this is just x to the 10th plus 2 dx. And so what is that? That's 1/11th x to the 11th plus 2x plus a constant. 3 very similar looking problems worked out in 3 very similar ways, but because of the subtlety of the differential, 3 very different answers. Moral of the story, the differential matters. It's not just an appendix that's placed at the end of our integral. So here we go. What happens when we try this thing? Now, some of you are already saying to yourselves, I know what this is. This is the derivative of sine of x squared. 2x cosine x squared is the derivative of sine of x squared, because the derivative of sine of something is cosine of something, and then we tack on the derivative. That's chain rule. That's wonderful. And if you already know that this is sine of x squared plus a constant, you may click ahead. I don't know how you would do that, but you would click ahead. What I would like to do is I would like to think to myself, can I get this to look like f of u du? And if I can do that, is this integrable easily? So here's the way we play this game. Because I want to make a substitution for u as a function of x, I'm going to select a u so that when this all shakes down, what I have is just a function of u. And the easiest way for us to do that is to let u be x squared. As a moral of the story, things in parentheses, things under radicals, they make very good u's. So I'm going to let u be x squared. If I let u be x squared, then the differential du is 2x times the differential dx. If you don't believe me, the derivative of u with respect to x is 2x, and then we cross multiply. So what does this integral turn into? Well, the cosine of x squared becomes f of u, and all the other stuff that's left is the du. So what have I got? I've got the integral of cosine u du. The cosine x squared is replaced by cosine of u. The 2x dx is replaced by du. And what we have managed to do is a complete change of variable. Everything that looks like x is gone. It is replaced by something that looks like u. I mean, not u. Now, the upside for us is that the integral of cosine u is very easy. The integral of cosine u is sine u plus a constant. And I know what u is. What you are? No, what u is. That's the sine of x squared plus a constant, which is exactly what we thought this should have been in the first place. All right? All right. How about the integral of x times the square root of 5 plus x squared dx? That can't be hard. So again, things under radicals make for good u's. And since things under radicals make for good u's, I mean, I'd really love to turn this into f of u du. We're going to let u be 5 plus x squared. Why? Because du is the derivative of 5 plus x squared. That's 2x dx. And so I'm thinking to myself, what have I got? The radical becomes radical u, and that's easy to integrate. The problem is I have an x dx when I need a 2x dx. And so, oh my gosh, how are we going to do that? Again, as mathematicians, we creatively multiply by 1. And we multiply by 1 in such a way that this is part of the du that we need, and this balances that out. So the 2x dx gets replaced by du, and the 1/2, that's outside. So now how do I take the antiderivative? The antiderivative of u to the 1/2 is 2/3 u to the 3/2. And so that's 1/3 u to the 3/2 plus a constant. You're starting to sense the moral of the story. And the sense of the moral of the story is, if I ever have a part of an integrand whose derivative or a constant multiple thereof is somewhere else in the integrand, u-substitution is going to work really nicely. Really nicely. Permit me to get a little bit weirder. Just a scotch. Just a scotch. This is admittedly tricky on purpose. This is the kind of thing where we look and we say, oh boy, oh boy. See, I don't have anything in here that's the derivative of something else in here. Like, if I thought that cosine x would be the u, then the du would be negative sine x, and that's just not there. I'd love for there to be a sine x in the problem, because the derivative of sine x is cosine x. So, I mean, I really want this to be something like this, where that is your du. I'd really like for that to be the case. But to do that, I would need this part to be in terms of sine. Oh. Oh, the mothership. Oh, I love me the mothership. Oh, yes, I do. And so what happens in this problem? We're going to let u be sine x. And then du is the derivative of sine x dx. Really, du dx is cosine x, and we multiply through. So what is this problem? 1 is 1. Sine squared x is just u squared. Do we see that? Do we see that that's u squared? And then the cosine x dx, well, that's just du, and I can do that problem. The integral of 1 is u, the integral of u squared is u cubed over 3 plus a constant, but we didn't have the problem in terms of u, we had it in terms of x, and so we express our answer in terms of x. Now, admittedly, that was a little tricky. I'm going to go 5 more minutes. So if you have somewhere to go and you want to do 5 minutes later, that's totally cool. But what happens if there are numbers? What happens if there are numbers? In fact, I'll tell you what, there's only about 5 minutes left, maybe 6 or 7. And so if you want to hit pause and just finish watching this tomorrow, it's totally cool. And if you have 6 or 7 minutes right now, it's totally cool, because tomorrow there won't be a video. So right now, if you want to do 6 or 7 minutes tomorrow, that's totally cool. No harm, no foul. I would like to do a u-substitution. And to do that, I pick something in the integrand whose derivative is also in the integrand. I'm going to pick sine x, and then du is cosine x dx. Really, du dx is cosine x, and we multiply through. So this part is the u, and this part is the du. We do a complete change of variable. This is the integral of u du. Now, folks, we do a complete change of variable. A complete change of variable, which means that these have to go. Oh, that was terrible. These have to go also. Those are x limits. We want u limits. So what does that look like? Well, when x is 0, what is sine of 0? That's 0. And when x is pi over 4, let's see. When x is pi over 4, what is the sine of pi over 4? That's radical 2 over 2. Those are your limits. We're going to integrate from 0 to radical 2 over 2. Complete change of variable. All the x's out, all the u's in. So how do I do this? Well, I take the antiderivative, I sub, and subtract. Radical 2 over 2 squared is 2/4 divided by 2 is 1/4, and 0 squared over 2 is 0, and I get 1/4. That's not bad. That's not bad at all. All right, I'll go one more. That was 5, this is 6. I'll go one more and we'll call it a video. Going to do the integral from 0 to 1 of 3x squared over x cubed minus, oh heck, 9. Boy, I hope this works. So this is a dead giveaway because we clearly have a part of the problem whose derivative is in the problem. And so we clearly know what our u is going to be. Denominators make great u's, by the way. Great u's. So we've got du is 3x squared dx, which means that I'm dealing with the integral of du over u from, if x is 0, u is -9, and if x is 1, u is -8. Well, what's the antiderivative of 1 over u du? It's the natural log of the absolute value of u from -9 to -8. We sub, and subtract. And then when you check that answer in the back of the book, they're going to write it like this because that's going to save them space. And you're going to say to yourself, why can they do that? Oh, I get it. I get it. So what we're going to do in class when I see you for the next couple of days is we're going to practice getting really good at reading u's and du's. All right? All right. Awesome. Thanks, everybody.